Welcome to section 4.1, talking about quadratic functions and transformations. This should be very familiar to us from some of the previous sections we've covered so far this year. But I did want to mention this objective we have right here to identify and graph quadratic functions. If you guys recall, we've been doing a little project, not a project, but a little approach this year called NAGS. And that's going to, again, stand for numerical, algebraic, graphing, and summary. Well, this is going to come in awfully handy for these quadratics, because if you haven't noticed, when you're able to complete all the NAGS on these functions, you're really describing everything you know about it. The actual algebraic expression, what the t-charts and plots would look like, what the graph would look like, and then in the summary be able to describe what the graph is showing us. These are some nice little definitions that you guys would probably want to copy down in your Cornell notes. A key concept for this section is going to be basically what does a quadratic function look like and how is it transformed and what are the parts of a quadratic function. So if you look at this key example, it talks about the parent function being x squared, and its graph is shown here below. The axis of symmetry goes right through the graph, creating a mirror image on either side, and the vertex here is going to be 0, 0. Axis of symmetry is going to be your h value for your vertex, and that's the basic components of a quadratic function. Let's go down and take a look at another example of a quadratic function. Here we were asked to go ahead and graph this function right here. And what we did was, or what I did was, I went ahead and drew in red the parent function, y equals x squared. And then from there, I moved the vertex of 0, 0 over 3 to the right and up 4. Over 3, up 4. And I also was able to move the axis of symmetry over 3 units, very similar to this value here for h. Again, this is h, this is k. Always take the opposite of what you think h is, and k is what it is. And this would be a nice little description of a NAGS. We've got a numerical, we could probably go ahead and create a t-chart and plug all those values in, but we went ahead and did a quick graph by looking at just the vertex and its shift from the parent function. We also were able to describe the axis of symmetry, and if you look at these graphs, this is called, by the way, concave up. And again, you probably figured out if you had a graph something like this, it'd be called concave down. I wanted to add those two in here for our future NAGs on these quadratics. So let's go ahead and actually do a full NAGs on a quadratic function. And a real basic one, y equals 2 times x squared. Numerically, we can go ahead and plug some values in here. If you recall, this is going to be just really 2 times the parent function, and the parent function has a vertex of 0, 0. So all we're going to be doing is just picking a couple values to the right and a couple values to the left of the vertex to go ahead and graph this. And lo and behold, when we have these real basic functions, the Fab 5 work out very well. So let's plug in -2. That's going to be 2 times -2 squared. -2 squared is 4 times 2. That's going to equal 8. Let's plug in -1. -1 squared is 1. 1 times 2. It's going to spit out a 2. Plug in a 0. Going to spit out a 0. Plug in 1. Going to spit out a 2. Plug in 2, it's going to spit out an 8. Now let's go ahead and look at this algebraically, of course. simply y equals 2 times x squared. That's going to be your algebraic expression. We actually solved for y on that one. Now let's go ahead and graph these coordinates. Negative 2, 8, negative 2, 8, negative 1, 2, negative 1, 2, 0, 0, and then 1, 2, and 2, 8. Hopefully you have noticed that the graph, again, is split by the axis of symmetry right here, which is the same thing as your vertex of 0, 0. Our axis of symmetry right here is going to be the equation x equals 0. This is the line x equals 0. It's also known as the y-axis. Again, axis of symmetry, awfully helpful. It helps us create a mirror image of the graph. This is 2 units away, that's 2 units away, this is 1 unit away, that's 1 unit away, and we get this nice smooth curve not really smooth, but good enough for us, of the equation 2x squared. So now let's go to our summary. Our vertex, we said, was 0, 0, and we had a stretch, or excuse me, our axis of symmetry is going to be x equals our h value, which is 0. We had a stretch or a compression. Well, the stretch, a was greater than 1, therefore it was a stretch of 2. There was no compression, and we had a concavity, I should say, is concave up. Let's take a look at refamiliarize ourselves with the translations of the parent function x squared. In the book, they went ahead and took a look at 2 different types of translations. One, here they're subtracting 5 from the entire parent function. Here, they're subtracting 4 from the x value within the parent function. Remember, when it's outside the parent function, it's a vertical shift. This case, down 5, parent function, shifted down 5 units. Here, they had a horizontal shift. You want to do the opposite of what you're thinking. You're thinking this is left 4, but actually it's to the right 4. So what they did, they moved this whole thing over 4 units. They moved all these points over 4 units. Every point on the red graph was translated over 4 units. Here they talk about the axis of symmetry. It's still, the vertex is 0, 0, the vertex is 0, 5, but remember your axis of symmetry is related to your h value. Here, your vertex was 0, 0, that was your axis of symmetry right here, and your axis of symmetry here is going to be your new h value for your vertex at x equals 4. Let's go ahead and perform a NAGS of a quadratic function and answer all the questions in the summary section. They want to know the vertex. I'm going to highlight these. They want to know the vertex, the AOS or axis of symmetry, the maximum or minimum contingent upon concave up, concave down, the domain, and the range. Numerically, we can go ahead and plug some values in. Let's first find our our vertex. Our vertex is going to be HK, remember. Sorry about that technical difficulty there. There we go with the vertex. So our vertex is going to be HK 4, negative 2. So I want to pick 2 values to the right of 4 and 2 values to the left of 4. Well, let's see. 2 and 3 are to the left, and we got 4, and then 5 and 6. Now let's just plug those in and see what happens. Plug in 2. 2 minus 4 is negative 2. Negative 2 squared is 4. 3 times 4 is 12. 12 minus 2 is 10. Plug in 3. 3 minus 4 is negative 1. Negative 1 squared is 1. 1 times 3 is 3. 3 minus 2 is 1. Plug in 4. 4 minus 4 is 0. That's going to leave us with negative 2, as we've stated already. And 5. 5 minus 4 is 1. 1 squared is 1. 3 times 1 is 1. 3 minus 2 is 1. Plug in 6. 6 minus 4 is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 2 is 10. And algebraically, again, we've got our nice handy-dandy little equation here. Next, let's go ahead and graph these puppies. 2, 10. 3, 1. 3, 1. 4, negative 2. And we're going to have 5, 1. And then we're going to have 6, 10. Again, creating a mirror image, so it's nice and easy for us to find our axis of symmetry right here. And if you recall, our axis of symmetry is going to be related to our vertex. Our vertex was, if I'm not mistaken, 4, negative 2. Axis of symmetry, x is going to equal 4. Let's go ahead and graph this. Nice smooth curve here. Make a little smiley face, and then let's connect the smiley faces. Continue these graphs on because they go on forever and ever. There's our graph. This is concave up, so that means we're going to have a minimum. Our minimum's right there at the vertex. But the thing they want about the minimum is really what the y value is at your minimum. It's our minimum output. We don't have a maximum output, unless you would call that infinity, which I would. And then let's talk about the domain and range. So the domain are all of our possible x values, if you recall. And that means I can plug in any x value here, and it'll spit out a value all the way up here on the graph, which it will. So my domain is going to be all real numbers, all reals. The range, however, are our possible y values or our possible y outputs. Now, it does have a limit. You will not see anything below this line right here at y equaling negative 2. So our range is going to be y is going to be greater than or equal to negative 2. And that's all they want from the range. You guys get the joyous task of doing your own little nags right here for this function. Again, that's your a value, remember. This is your h value, and then your k value. First, let's find our vertex. It's going to be 1, 3. Then, go ahead and pick, I'll give you a heads up here, get some values for x and y. Pick 2 to the right and 2 to the left of 1. Well, to the left of 1 is 0, negative 1. We can also plug in 1 there also if you'd like, and then pick a couple points to the right of 1, which is called 2 or 3. And then what you're going to have to do, again, is plug those in to find your numerical values. Graph this, and then write yourself a nice little summary. That's probably going to be the vertex. That's going to be the axis of symmetry, max or min, and up, concave up, or concave down. Folks, have a good night.